Okay, chalo. So today we discussed Newton's third law. Third law of motion. Right. The first law has been discussed, the second law has been discussed, but if we see it in a little bit of a summarizing pattern, then the first law actually tells you what is the definition of force. That if a force acts on a body, it can change the state of the body. If the body was at rest, it brings the body into motion. If the body was in uniform motion, it can change the state of uniform motion. The first law also tells us about something about net force, that if you have net force, then there is an acceleration which is there. The second law tells us how to quantify that force. This net force is given by the product of mass into acceleration and is also said to be the rate of change of momentum, that is final momentum minus initial momentum divided by the time elapsed gives you what you call as the force. Yaad hai to? Now you are getting forgetting. Yeah, because this could have pulled it so strongly now. Right. Okay. So, hey, come on. Once the class starts, please don't talk. See, I'm all fine. You gossip till the class starts. Once the class starts, please don't. And that's becoming a bad habit day by day. Okay. So the force by the second law is given as the product of mass and acceleration. This is one. First law tells you about force. Second law quantifies force, okay? And we also got another definition of force, that force is equal to the change in momentum, delta P over delta T, where we say delta P is P final minus P initial divided by delta T. So this was mv minus mu divided by delta T, which was the mass into v minus u by delta T. Finally, this is mass into acceleration, right? So when we were talking about these two forces, the first law and the second law, now the two forces, the two laws, we were always seeing a body. Now, common diagram that I should draw, a body and a force acts on it. So body was just like a slave, you take a body and I have every time force acting on it. Third law, for the first time, analyzes the body's perspective. That is, can you always exert a force on a body? Is it that sort of a slave? Does the body have no right of freedom or anything? So in humorous tone, we say the third law for the first time allows the body also to express its retaliation, right? So it means till the first law and second law, we used to have a body and we used to happily draw this diagram that a force is exerted on the body. The third law for the first time says that the body can also exert a force. If you exert a force on the body can also exert a force. Now that everyone is very much aware of this third law, they say every action has equal and opposite reaction. Now that's from literature's perspective. Physics, it's not that easy as a definition. It's not that easy as a definition. Every action has an equal and opposite definition. The first thing here we should understand before going to the law is something called action-reaction pair. Action, and pay utmost attention if you will be having physics in your grade 11. You will not study all these things in grade 10. The next year you will study is grade 11. Action-reaction pair. Action-reaction pair. So the action is one type of force. The reaction is also force, and both force form a pair. Now what are these type of force? Action-reaction will be one of your most important and vital thing when you will be studying free body diagrams. When it means in grade 11 we have something called a free body diagram. People get a lot of confusion in drawing a free body diagram. So let's understand this. Action reaction, the first criteria is the forces have to be of the same type. If you classify two forces to be of action reaction pair, the forces should be of same type. Now what do I mean by type? If this force is electromagnetic, this force also should be electromagnetic force. If this is gravitational, this should also be gravitational. If this is frictional force, this should also be frictional force. If this is normal reaction, this should also be normal reaction. Are you understanding this? So let's have a quick look at some common type of forces that we encounter in daily life. Okay, some common type of forces. Now, the first force is weight. The first force is weight. Types of forces. Now, what is weight? This is the earth. The earth pulls every body towards its center. Right? The earth pulls every body towards its center. To pull this, the earth also exerts a force. And the definition of force is what? Mass into acceleration. Though your gravitation chapter has been taken away, but just assume there is a special class of acceleration called G, acceleration due to gravity, mass into acceleration. And this special force is called weight. Or you can also call this as the gravitational force. Now, since gravitation as a chapter has been taken away, but let's understand. Law of gravitation says every body in this universe attracts every other body. It's not that the earth is only attracting an apple towards it. No. Apple is also attracting the earth. And the most stylish thing is both the forces are equal. That's what Newton says. Now, when you studied like every action has equal and opposite reaction, then you are not able to appreciate these things. So we have to appreciate these things which are now seeming a little bit difficult. How can the apple attract the earth? It happens. Are you attracting that particular computer trackpad right now? Yes. Is the computer trackpad attracting you? Yes. Yes. But we don't see you getting attracted towards it. Otherwise, you and a buffalo walking on the road, you should have been attracted towards the buffalo, or the buffalo should have been attracted towards you. We don't see that happening, but it happens. So before understanding Newton's third law of motion, we have to understand action-reaction pair. What are action-reaction pair? Two forces which are of the same type. Number one, these forces should be of same type. Number two should be equal in what happened? They should be equal in magnitude. And third should be opposite in direction. This is somewhat now trying to hit what you try to say. Every action has an equal and opposite reaction. Just see. Two forces which are of the same type, equal in magnitude, opposite in direction. Only these forces will be called as action-reaction pair. I am exerting a force which is a muscular force on a body of 5 Newton east. Body is at that time giving a frictional force of 5 Newton west. They are balancing forces but not action-reaction pair because the class of the forces are not same. Have you understood? For action-reaction pair, look, there's a body which is experiencing a force of 5 Newton on the west side and experiencing another 5 Newton force on the east side. These are balanced forces. Do you have sufficient information to say that this is an action-reaction pair? We don't, because I have not classified what is the type of the force. If this was, say, a force due to electrostatics and this was a force due to electrostatics, then these are balanced forces plus form an action-reaction pair. If this was a friction force and this was a friction force, then action-reaction pair. If this was a normal reaction force and this was a normal reaction force, action-reaction pair. Have you understood? Let's understand the concept of weight. The weight is a force which is a gravitational force where Earth is pulling the body towards itself. At the same time, as of now, just appreciate it, the body is also pulling the earth towards its center. I'm saying this is the gravitational force of the body, and I'm saying this is something your heart will not agree initially, the gravitational force of the earth. Both are equal, but we always see the apple coming to the earth. We don't see the earth going to the apple. Very simple. Force is mass into acceleration. 6 can be written as 1 into 6. 6 can also be written as 6 into 1. Force is mass into acceleration. The mass of the earth is much more. Therefore, the acceleration experienced by the earth will be less. So the earth does not seem to go towards the body. The body's mass is less, so the body comes towards the earth. Take a magnet and take a small nail. Just leave them. You'll see the nail getting attracted to the magnet. But take a big nail and take a small magnet. The magnet will get attracted. The force is same. Magnetic force, same force, opposite in direction, equal in magnitude, action-reaction pair. Have you understood what is an action-reaction pair? All of you. Two forces which are of same type, same magnitude, opposite in direction, constitute what is called an action-reaction pair. Unless and until you understand action-reaction pair, you will not understand what is Newton's third law. Clear? Any confusion on action-reaction? Okay, let's see one. So weight was one sort of a force. Weight is a gravitational force. Weight is a special name given to Earth's gravitational force. When Earth pulls a body towards itself, we call it weight. Let's go to the solar system. Isn't the Earth pulling Venus? Yes. Isn't the Venus pulling Earth? Yes. We call them as gravitational forces. We don't call them as weight. Weight is typically when you are on planet Earth and everybody is being pulled towards the center of the Earth. Have you understood? We'll go to weight, and although the chapter is taken away, but we'll discuss. Otherwise, the concept will not get clear. So, weight stroke, I am writing gravitational forces. Have you understood gravitational forces? Right? So, right now, this mobile phone is being attracted by the Earth. The Earth is also being attracted by the mobile phone. Your heart does not agree, but that's true. Shall we see one more type of force? Okay. Another type of force is known as normal reaction. And this is where the entire confusion happens because the books make a wrong diagram. Normal reaction. Let's see where normal reaction comes into. Let's say we have a body. Okay. And this body is placed over a platform. This body is placed over a platform. You right now forget Earth, forget every other thing. This body is placed on this platform, right? What we will see is that whenever think yourself to be the horizontal platform, and on that horizontal platform, the square body or the cuboidal body has come, right? Immediately, this horizontal platform will give a normal reaction. Normal reaction is always normal to the surface in contact. So I will have a normal reaction in this manner, and let me name this body as say 1 and this body as 2. I call this force as, this is a normal reaction Fn, and I call this as 2 1, means normal reaction exerted by 2 on 1. Two bodies in contact. Acha, why are you being so stepmotherly with body 1? That body 1 is also in contact with body 2. So body 1 will also exert another normal reaction on body 2. Okay, so let's draw that normal reaction also. So you will have another normal reaction which will go downwards. And these two forces will be exactly equal to each other. So we call this as Fn 1, 2. What are the type of forces? Normal reaction. Are they equal in magnitude? Yes. Are they opposite in direction? Yes. Do they constitute an action-reaction pair? Yes. Understood? Now it's time for us to go to Newton's third law. So let's listen. Don't write Newton's third law immediately. Okay? Newton's third law says, suppose you have, let's first understand it through diagrams. Okay, why am I drawing? Okay. This is body 1 and this is body 2. Okay? So far we used to study when a force acts on a body. When a force acts on a body, body was never given any chance to retaliate. Now we'll give it the chance to retaliate. So Newton's third law says, when a body exerts a force on another body, watch my wordings, okay? When a body exerts a force on another body, the force is vector, so I'm putting a vector symbol. This does not show direction, this shows this is a vector. This force is going on which side? When a body exerts a force on another body, now come this side, the second body exerts equal and opposite force on the first body. So I can use colors out here, otherwise I'll not get the arrow. The second body exerts equal and opposite force on the other body. So this is F21. So we can write, in vector form we write, F12 is negative of F21. Negative means both the vectors have equal magnitude, their forces are equal. Negative means their directions are opposite. So in other ways, you can write that F12 as a force, and if you add F21, you get it 0. Such two forces constitute what is known as an action-reaction pair. Constitute an action-reaction pair. Even the diagram in Lakshmi Singh is also not correct for students to understand. Now, what you learn Newton's third law every day is that when a body, every action has an equal and opposite reaction. That's literature. In physics, we say when a body exerts a force on another body, the second body exerts an equal and opposite force on the first body. Now go back to the earth and the apple example. Is the earth a body? Is the apple a body? So Newton's third law says when a body, earth, exerts a force on another body, that is the apple, the second body exerts an equal and opposite force on the first body. That means the apple must also be attracting the earth towards itself. In like this is motion going on. Our next chapter earlier used to be gravitation. There we used to study the first law used to be Newton's law of gravitation, or we used to call it as universal law of gravitation. We'll study that law. That law is an extension of this law itself. Only it is limited to gravitation. Only it is limited to gravitation. When a body attracts another body, change the wordings. When a body exerts a force on another body, the other body exerts an equal and opposite force on the first body. So can I not say when a body attracts another body, the other body... On this we used to do lovely problems also, which you will laugh like anything. Itna samajh mein aaya? Understood? Now let's see some impact on it. Say for example, this is the ground, all right? And say a person who is doing push-up. What are you doing? You are exerting a force on your body number 1. You are exerting a force on body number 2. Body 2 is exerting an equal and opposite force on. That's how you are lifting up. When you sit on that chair with wheels around, why do you hold your table and then slide and go? Like Adya is sitting right now, or Ahan is sitting right now. They must be sitting with chairs which have got wheels. You just hold your table and you go. When a body exerts a force, on another body, the other body exerts an equal and opposite force. So what force did you give? You gave a muscle. Now you have to see, you have to find out that the two forces should be exactly similar to each other. So that's a contact force. You're giving a contact force on the table is delivering a contact force back to you. Have you understood? Let's see one more example out here. Let's say that this is the shore, and out here I have got, this is a river, right? And the boat actually brings you till this position, all right? And look here, there is this person, right? And imagine that his leg is a little bit, okay. The person, in order to get out of the boat, what does he do? He pushes the boat. You push the boat. Friction force. When a body exerts a force on another body, then what happens? The other body exerts an equal and opposite force on the first body. That's how you come out. At that time, if this boat would have slid away, this fellow could not have come up. Imagine. How do you walk? You try to push the road through a frictional force. The road pushes you forward. If you were trying to walk on this floor wearing socks, which we used to do in our childhood after seeing Winter Olympics, what happened? Soye hue ho tum. And we would have worn, we used to wear socks and put talcum powder on the floor. And then we used to do Winter Olympics in our house. After seeing Winter Olympics, we used to be very much, excited. We can't get snow. So put talcum powder on the floor and put socks. Now you try to walk. when a body is trying to exert, you're not able to exert the force. So these are examples that you get in books of CBSE. Now, would you see how you get nice examples in, say, books of Cambridge and IB? Now, see a lovely example, okay? Now, let's say, this is a beautiful example. Let's say you are on orbit, and this is the International Space Station, ISS. I hope you all know what is the International Space Station, right? So this is the International Space Station, and we can exactly do problems based on the knowledge we have. And there is an astronaut who is right now outside and performing some repair works out here. There's an astronaut outside who is performing some repair works out here. And he suddenly finds that he has some worth 2 minutes of oxygen left with him, right? And the separation is some, say, distance s from him and the space station. Now, the space does not have any medium like air or something where you can surf or swim, all right? So have you seen sky surfing and skydiving? There also the people can go up and go down, because till the time your turbulent velocity, your terminal velocity is not reached, you can do those things. But in the space, you can't do. Now, this fellow his oxygen content is dying out. And he knows that his oxygen, content left is for 2 minutes. And he still is H distance apart from the space station. How does he get into this? So they will say that while he was walking, he is also carrying a hammer with him. And the mass of this hammer is something like, say, the mass of this hammer is mkg. They'll ask you, with how much force has to he throw this hammer? Yeah, when he throws the hammer, he exerts a force on the hammer will exert an equal and opposite force on him. But make sure the direction should be same. You can't expect the space station door to be here and you throw the hammer here, then he will be lost in space. They do this. So he has to throw the hammer with a force so that he is guided here. So I know what is the distance. S equal to ut plus half at square, you'll get the value of the acceleration that you need. Once you get the value of the acceleration you need, you can find with what force you have to throw. Very nice and interesting problem. In fact, they will give you some forces like some drift speed, some small drift speed, and that drift speed will coolly take him inside. Have you understood Newton's third law? Now let's see where people get Newton's third law wrong, okay? And where there are many books who actually draw it wrong. Same example, this is a tabletop, okay? This is a tabletop. Sorry. This is a tabletop. Okay, and on this tabletop, I have kept some object out here. Let us try to, if we have understood Newton's third law, we should be able to see two scenarios out here in a proper manner. Let's see the two scenarios. Okay, I'll replicate this diagram also. So let's say this is one more diagram. Okay, and let's see the forces. At the first instance, we won't see any sort of weight or gravitational pull. We'll just see them. This is called free body diagram. You take out everything and just keep these two bodies in space. Are these two bodies in contact with each other? Yes. If they are in contact with each other, normal reaction will come into force. So let's look at the normal reactions. Now, normal reaction forces always originate from the surface in contact. Okay, there will be one normal reaction here, and there will be a normal reaction here. And you can open your books later on and see where it goes wrong. So this is the table and this is the block. So this is the, what is this normal reaction? This is the normal reaction of the block. Block is saying, table, get out of me. Get out of me. It's reacting. Get out of me. Yeah. So this is F, I'll say BT. And this is F, TB. Both of this is the case of normal reaction. Normal reaction. Have you understood? They constitute a action-reaction pair. and they can be used as an example of Newton's third law. This is a classic example of Newton's third law. Okay, so wait, let me replicate this. We have to draw one more diagram also. So let's keep one more diagram here, and let's take this diagram and let's, what happened? Okay, so we'll just reduce this diagram size. This you have understood, right? So let it be here. Okay. Now, have you understood this? Correct. Okay. Now, don't you think that this table is actually resting on Mother Earth? The table is resting on Mother Earth. And Mother Earth, let us assume that this is the center of Mother Earth. Very, very hypothetical scenario, as if it's so close to the center of the Earth. This is the center of Mother Earth. So what will happen? The force of gravity will work. And the force of gravity will work on which one? The table. And it should act on the book also. Okay, so let's see. Okay, so how it happens is, let's see it for the table first. The force of gravity always acts from the center of gravity of a body. Center of gravity is that point from where the force of gravity is acting. Now you might be thinking, what is the center of gravity of a solid sphere? The center of the sphere. What is the center of gravity of a solid cube? The center of the cube. But if I ask you, what is the center of gravity of a nut? Center of the nut, which is nowhere in the body. Which is nowhere in the body. The center of gravity of a hula hoop is the center of the hula hoop, which is not in the body. Very interesting, yeah. So we expect now that the gravitational force for the table is working from the center of the table. Understood? So what do I call it? I'll call it the gravitational FG, gravitational force which the Earth is attracting the table, PT. Am I clear? Okay. Don't you think that, okay, let's for some time just take this away. Okay, just I'm taking this away. Say the block is not there. Anyways, the diagram means the same thing. The table will also be attracting the Earth as per Newton's third law. Newton's third law says when a body, Earth, attracts or exerts a force on another body, the other body exerts an equal and opposite force on the first body. So in this case, there will be another force, and now it will be attracting the Earth directly from where? From the center of the Earth. So we have another force out here, which is F. I'll call this as F, and I'll call this G, the table exerting on Earth. Is this an action-reaction pair? Yes, this is an action-reaction pair. Okay, and then I say, can this be used as an example of Newton's third law? Exactly. Where we go wrong is, we go wrong in these type of diagrams. They will show that the weight or the gravitational pull is being balanced by, the reaction. Is there in this book also, but that's not correct. What I'm trying to say, would you expect what you call weight of this particular block? It will be acting right from the center. Now this is what type of force? This is a gravitational force. If you are trying to balance it with normal reaction, then normal reaction acts from where? From the surface. No. Surface. This is the normal reaction force. They are generally equal. Just imagine my hand has got a weight. I'm putting a weight on this table, or I make a puppy sit on this table. The puppy is exerting its weight on this table. The table is exerting a normal reaction on the puppy. Is the puppy flying away? No. Is the table breaking down? No. They are balanced forces. They are balanced, but they are not action-reaction pair. That you need to understand. Do you understand? If instead of the puppy, I bring a newly born elephant baby on this table, what happens? The table breaks because the normal reaction is not sufficient to balance the weight of the elephant. So they are not, in that case, balancing anyway is not there, but they are not action-reaction pair. Books will write what you know. This is weight and this is normal reaction. This is Newton's third law. This is not Newton's third law. For Newton's third law to happen, the forces have to be of the same type. It is not necessarily that they should always balance and be in opposite direction. This part, generally, they don't deal in grade 9, and they are very fine to give you marks if you write every action has an equal and opposite. At least I will not give you marks. Because when you say every action has an equal and opposite reaction, all these statements are never spelled out when a body exerts a force on another body. So have you got a fair bit of idea of it? So shall we write now? Now you can write. Now you write Newton's third law. Newton's third law states that when a body exerts a force on another body, when a body exerts a force on another body, the second body exerts an equal and opposite force on the first body. The second body exerts an equal and opposite force on the first body. The second body. मैं समझाऊं, एक इजी एग्जांपल से समझा दूं, पूरा समझ में आ जाएगा. समझे? मैं खींच के एक चाड़ा तुम्हारे गाल पे मारता हूं. सुनो 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 ना, मजा लो ना. So you feel that I have hit you and I have hurt you? No, I will get equal amount of pain. When a body, see, you'll remember for your whole life, when a body exerts a force on another body, the other body exerts an equal and opposite force on the first body. The thing is that since I am elder to you by age, and say my built-up is more than you, resistance is more, muscle is more stiff, the force which your cheek is going to exert on my palms may not cause pain to me. Are you understanding? However, let's reverse this example. Understand physics like that. If I bring a toddler who is 1 year old and you are sitting like this, say you're sitting like this, and the toddler hits you on your elbow, don't you think the toddler will receive the pain? Yes. Because, and you don't receive the pain. Pain is a different part. Pain is your response to how much you can withstand. But the force with which the toddler hit you was exactly same as the force that your elbow joint exerted back on the toddler's palm. However, in reality, we will see the toddler crying. And in the former example, we will see you crying. Because if I give one chata to you, it is, till the time the video signal comes, it is barely, it's unlikely that I will cry. Right? That's why people slap on cheek. That's why people slap on cheek. The thing is that the pain is always felt by the portion which is more softer. But the force will be same. Sometimes when people, sometimes there will be some teachers and some people, nowadays you all don't get thrashed. That's why you don't have that experience. In our days, when we used to grow up and our dads used to thrash us, they used to say, you become a rhino day by day. Hitting you, I get more pain. That's because your body is now becoming stiffer and stiffer. Have you understood? But that slap on the cheek, is it an example of Newton's third law? Exactly. Contact force, equal and opposite. And if we bring our head to head, same mass, same structure, same build up, and you know, in our days, our school teacher used to do, if two children talk too much, she used to hold the heads together, and at that time the pain will be equal. The pain will be equal. The masses are same. Thak, thak. Is it an example of Newton's third law? Yes. Have you understood what is Newton's third law? Very good. So have you written it? The second body exerts an equal and opposite force on the first body. Such forces constitute an action-reaction pair. Such forces constitute an action-reaction pair. Write that. And also write, for forces to team up as action and reaction, following criteria must be met. For forces to pair up or team up as action-reaction pair, following criteria must be met. What are the criteria? You yourself know. Type of forces should be same. Magnitude should be same. Direction should be opposite. Okay? Now everything clear? Nitya, clear now everything? So don't keep on writing the definition first. First understand. Once you understand, it will be very easy for you to even write it, because you know English better than me. Yeah. So let's try to marry Newton's third law, Newton's third law versus momentum. Let's just see momentum. There's nothing to mug up if you understand the concept. Newton's third law versus momentum. For Newton's third law to be active, two bodies should be there. It should be a two-body system. Two-body system. So I should have a body A and I should have a body B. Body A will exert a force on A, which is known as FAB, and similarly, B will exert FBA. Have you understood? Okay? Now, see it from the perspective of only body B. Body B must be in some state of motion, rest, or maybe in motion. Suddenly, a force came and acted on it. Once a net force comes, there will always be an acceleration bond. There will be a velocity which might be imparted to it. So don't you think that body B will have a chance to have a gain in momentum, which I call the momentum of the body PB? Hey, I'm fed up of this. I don't know. This keeps happening in this class so much. Grade 10, this never happens. And grade 8, it happens. Never it happens in grade 10. So body B has, again, this is all because of this OBS. I mean, it will come up. 1 minute. I changed the whole system. Okay. Body B is actually experiencing a force. Means it will have some velocity. Don't you think there will be a gain in momentum? Right? At the same time, if there is a gain in momentum on this, don't you think on this side also there should be a gain in momentum? Because this body is also going to experience a force. Momentum is a vector quantity. If there is a gain in momentum on this side, and there's a gain in momentum, so the net momentum is 0. From Newton's third law, we actually get a concept, again, not in your syllabus, has been removed from that, which is known as the concept of conservation of momentum. Now, let it be. Conservation of momentum. Give me a minute, children. Is there? Okay, is there or not there? We will study. Otherwise, for me, it's a conservation of momentum. They write the word as momentum. But since you are in linear motion, I will add this word called linear momentum. Because in grade 11, you'll study another momentum, which is called angular momentum. Conservation of linear momentum. It says, you can't create momentum, you can't destroy momentum. If one body gains a momentum, another, not that. If in that, we call it as a system. System. In physics, we have got something called system and something called surrounding. Anywhere where your focus is and you are studying, that is all a part of system. Best way to understand is a refrigerator. Everything inside the refrigerator is system. Everything outside is known as surrounding. So the net momentum of a system, and system is always isolated, is always conserved. Right? A system may have 2 bodies or 3 bodies. Whatever is happening in that system, the momentum is conserved. Somebody may gain momentum, somebody may lose momentum, but momentum does not change. Have you understood? Let's take a small example of a rocket, and understand why is the rocket lifting up. We say that is Newton's third law, that there is forces of gases are exerting force on the ground and the rocket is lifting up. Not exactly. If you see a rocket, obviously a heavy body. A heavy body. I want this rocket to lift. I want this rocket to lift. If you have more momentum, will your motion? Momentum is a measure of the motion, we said. A bull walking on the road has momentum. A bull running on the road, more momentum. This is almost a bull. This bull has to lift up. Do you agree? So we have to impart a lot of momentum to it. Now, what is momentum? We have to impart a lot of momentum. We have to make this momentum high. That is the momentum of the rocket high. So what is the rocket's momentum? The mass of the rocket multiplied by the velocity of the rocket. Agreed? At this time, what we are doing, there are some very small nozzles. And through these nozzles, we are trying to get what? We are trying to get the gases out. And these gases will be coming out at a velocity of gas which is very, very, very high. Very high velocity gases are coming out through small nozzles. What is the mass of the gas? Less. But we will ensure that the mass of the gases is the gain of the momentum of the system. So there should be another gain of momentum on the other side. That will be gained by the rocket. And the rocket is a classic example, as I told you, where it continuously keeps on losing mass. Where is this gas coming from? It is coming from the rocket. So slowly, this is also 2 into 3, 6. That is also 3 into 2, 6. But slowly that 3 will get reduced because the mass is coming down. It will turn to 1 into 6. The velocity picks up like anything. Let's say, how does an aircraft fly? How does an aircraft fly? So we have got the jet engines. The jet engines will be fuming, the fuel will be burnt, and the burnt gases will be sent out through small nozzles at a very, very high speed, So when it's coming out at a very high speed, there is a momentum gain of the gases. So there should be an equal momentum on the other side also. The aeroplane gains momentum. Very heavy, right? And it starts to get, aeroplane works on 4 forces. One is known as the thrust. This is what we are talking about, thrust. Second is the pull. Then third is the lift. Okay, the pull, the thrust, lift, and another is the wind drag. So as soon as the aeroplane is going, what will happen? The wind will be flowing towards the aeroplane. And the winds is made to flow in such a manner, the aerofoils will then open up. So that the winds on the top side of the aircraft will be going at a very high speed, and at the bottom side it will be going at a low speed. This will generate the lift. That's why on stormy nights you see very light quality tins fly away. Have you understood? So that is also a principle of Bernoulli's theorem. That's what we use in a cricket ball to spin also. We will make one surface of the cricket ball very rough, and we will take another surface smooth. Whenever the ball is handed to the bowling party, the first thing they will say is shine Duke. If Duke is written there, they'll keep on shining Duke and make the other surface rough. So when the air comes in contact with the ball, the air will be going at a very high velocity on the smooth side. And on the bottom side, it will go with a slower velocity. This will induce the ball to swing. And the same thing happens. So you must have seen like bed sheets and other thing, tablecloths, when the fan is flowing at a very high speed, why does the tablecloth fly up? That's because on the top surface, the air will be going at a very high speed, and the bottom surface will go slow, and it will create a drag lift. Okay, so that's all. So the rocket flying is also an example of Newton's third law. And Newton's third law gives us conservation of linear momentum. So whatever momentum is being lost by the gases, lost means if you see southwards movement, there will be a gain in momentum on the other side as the rocket goes up. But let's see one more interesting thing which man has designed for the destruction of this world: the rifle. The rifle fires. The rifle is supposed to have a mass which is much, much more than the mass of the bullet that is ejects out. But what about the velocity of the bullet? Very high. So a bullet will be very, very low, less in its mass, but very high in velocity. So it is going to gain momentum. So it's going to transfer the same momentum back to the rifle. If the rifle was made light, by the time you fire, the rifle is going to वो पीछे आएगा ना, उसको भी तो आना है. It has, that's why it's heavier, but still it will recoil. This brings us to the most interesting scenario of problems which are known as problems based on conservation of linear momentum. So what does it mean? in these type of problems, okay, we will do many problems on this type. Problems based on conservation of linear momentum. What is momentum? Product of mass into velocity. So how these problems happen? For these problems to happen, we have to consider what is known as a system. Every problem can be brought into this analogy. First, understand what is the analogy. In the problem, these will not be there. They will say a truck collides with a car. So we have a system. In this system, we will have interacting bodies. And generally in such problems, you will have one body 1 and one body 2 interacting. This interacting will usually be in the form of a collision. And this collision you have to think as a sort of a event. What does the law of conservation of linear momentum say? It says that the momentum of this system is conserved. Neither can you add it nor can you destroy it. However, one thing may happen. In the whole house, Mishka gave 5 rupees back to her mother. Mother became rich, Mishka became poor. But has the house become rich? No. So there might be change in momentum out here, but overall momentum will be same. So there will be an event. All we need to target in these problems is momentum of the system before the event will always be equal to momentum of the system after the event. If you understand this logic, you can do every problem. You need not say, sir, why is the rifle taken 0? Why is the truck taken 0? Just so all problems will have some event happening. A rifle fires a bullet. Event. What is the system? Rifle and bullet. What is the event? Firing. Before the event means before firing. After the event, post firing. You have to find out what is the momentum this side and momentum that side. Unless you goof up on signs and all, you'll get a perfectly correct answers. If you try to memorize, you'll always land up in problem. Let's see one scenario on this. Okay, shall we? Let's see. Shall I change it? Okay, let's see one scenario. Okay, the scenario is, suppose there are 2 cars. This is car A and there is a sedan car out here. This is car B. Moving this side, moving this side. No issues? Okay. This is the good part. When you use a smart board, you don't have this facility. You have to keep on drawing. Okay. Oh. No, disadvantage because this was not an activated software. But the writing comes good, that's why I use this, okay? And our next one is नीचे नहीं रख सकता हूँ. Okay, नीचे नहीं रख सकता हूँ. Don't worry. Don't worry. Don't worry. Don't worry. Okay. Let's see this scenario. There is a car B which is moving in this direction. This car has got a mass. Let's say the mass of this car is MB. This car has got a mass. Let's say its mass is MA. MA is initially moving with the initial velocity UA. Very interesting. MB is moving with the initial velocity UB. Till this fellow was see something in his or her phone, and what happened? We say, Nazre hati, durghatna ghati. Okay, that's I will sue you in the court. All those things have now happened. I'll make a video out of it. Yeah. I'll make a video. This is okay. So in our problem, this is the event. The event is the collision. So this was going with MA. So let's see what is the momentum of the system before the event. It is, look, MA, which direction is it going? This direction. I use it as UA. Wait. Because it's going in this direction. Momentum is a vector. Which direction is this car going? Same direction. MB, UB. UB. Net momentum. Then there is a collision. There's a collision which has happened. And such problems assume that there is no loss of mass. No lamps broke. No bumpers fell down. No tires busted. But usually something will happen. There's no loss of mass. So finally what happens? We come to this scenario. And in this scenario we say, there can be many scenarios out here. After it has hit, let's say it gains a velocity in this direction itself, and I say this is VB, final velocity, and it is still going in this direction, and after hitting, this has also continued in the same direction. Possible, na? And then both are going in same direction. So this is VB. So VA. So what is the momentum of the system after the event? I will write MA VA plus MB VB. The law of conservation of momentum, this is only one scenario. The law of conservation of momentum tells me that if I say this is the initial momentum and this is the final momentum, we will say initial momentum will always be equal to final momentum. The whole problems are changed by scenarios. Now let's say I have a scenario in which after hitting this vehicle, scenario number two, after hitting this vehicle went in forward direction, he came back. So in that scenario, I'm changing my color now. It will be MA minus VA plus MV VB. Have you understood? There can be another scenario where it went and hit, and this is an Alto now hitting a army tank, and this actually stopped after the collision. He hit and came back. So it will be MA minus VA plus 0. Okay. Let's see another scenario. Both the cars are coming head on to each other. Head on. So in that case, the initial velocity would be MA UA plus MB minus UB, because it's coming in this direction. Then the hit happens, and after the hit, both go in this way. So in that case, we will say it is MA minus VA, MB minus VB. Problem can be changed as a defender of a football team is head-on striking with a striker. Defender has this much mass and striker has this much body mass. Their velocity says this. And after that, defender is pushed back. How fast do you think the striker will move? How far will you think the striker will move? That you have to do with this calculation. And you need not touch anything. You will just get the answer. Suppose you want to get the answer as VA equal to minus 3 meters per second. That means you'll see that the vehicle rebounds back with a velocity of 3 meters per second. Have you understood? There can be now, let's say, a rifle scenario. How do you see this in a rifle scenario? In a rifle scenario, what is the momentum of the system before firing? 0. Why is it 0? Mass of the gun into velocity of the gun plus mass of the bullet into velocity of the bullet should be equal to mass of the bullet into velocity of the bullet. Sir, who gave you the right to put positive? Arey, you idiot. bullet will always go in this direction, plus mass of the rifle into velocity of the rifle. This value will become 0. If you equate this plus this equal to 0, don't you think this value and this value will become negative? A plus B equal to 0. A plus B equal to 0. So A equal to negative B. So the rifle's velocity will always come in this direction, which actually proves us correct. So in our next class, what we will do, we'll take up problems now, and we'll do problems on this type. Okay? So on these problems, what do you have to do? First, make a diagram, whatever bad you can make, and try to find out what is the direct. The mass has got nothing to do. Mass, direction, or direction, or direction. Then there is an event. After that event, they will not tell you. They will say the small car went further ahead. What is the nature of motion of the car that hit the small car? So you will calculate the velocity of that car and you will get a sign. If the sign is positive, you will say that the body also moved in the same direction. So generally we say a guy who has more momentum transfers his momentum to the other, and the more momentum guy wins. Striker is always heavier than the coin in carom, right? The striker will come with a low velocity but has got mass. The coin has got less mass but more velocity, so the coin will fly away. Sir, can we not use the coin to hit the striker? You can, but you need a lot of velocity because you can't increase the mass of that coin. So so the idea is, say suppose you are being hit at the back, you are driving a simple sedan car, you are hit by an Alto and you are hit by a, say, a Toyota Innova. Where do you expect the damage to be more, considering both are of same velocity? The Innova will, because the Innova has more momentum. More momentum means, and how do you expect yourself to go along the direction of the Innova? Chel ke le jayega na. That's why if you see the structure and built up in football, how do you have? You will have two backwards, three backs, center and strikers. The strikers will be always lean and thin because they are supposed to sprint, and the defenders will always be very stout. So that when a striker comes and hits, he should just strike and fall. That's how it happens. Have you seen tug of war? Yeah. So in tug of war also, you'll put your dead load person at the last. So momentum बहुत high है उसका. Plus inertia also. In order to make him move is much more difficult. समझ में आया? So next class we will be doing problems on. You don't get problems on Newton's third law. We don't get any problem, but we get problems on conservation of linear momentum. And our class, Miss class, happens on 4th July, your favorite Independence Day. ठीक है? चलो.